Hello. Thank you for spending some time with us today. Over the next 30 minutes, you're going to learn how to create robust and secure application architectures in a fraction of the time you now spend creating quick and dirty prototypes. My name's Biff Gott. I'm a principal solutions architect and I've been with AWS for 7 years. To give you an idea how long that is in AWS time, it was at my first reInvent 7 years ago that we introduced what was then a brand new service called CloudTrail. Now this is a level 300 session, so for those of you who crave code, you will definitely be happy. How are we going to create prototypes that are more robust and more secure, and yet at the same time do it faster? We're going to accomplish this using two technologies, the AWS Cloud Development Kit, or the CDK, and the recently introduced AWS Solutions Constructs. Using these allows us to drastically change our expectations of prototypes, both how fast we can expect to generate them, and how complete we can expect them to be. So they say every good presentation should tell a story. So that's what we're going to do today. We're going to tell a story, a software fairy tale, if you will. And while our tale is not necessarily a true story, if you've been shipping software for any length of time, you will see the obvious truth within it. Once upon a time, there was an unassuming, mild-mannered hero. For us, that will be our developer architect. And every fairy tale needs an antagonist. In this case, our character is less technical and less heroic, but well-meaning nonetheless. Now, I don't want to vilify any particular business role, especially a business role that has direct control over my compensation. So for this character, I'll just make up a nonsense name. We'll call this character the Lanager. So our hero is responsible for the design and implementation of our company's primary game application. This game is an app running on mobile platforms that accesses REST APIs on the back end. Our hero realizes there's a potential revenue stream if people can buy game artifacts right from the game app. They can spend money to purchase gems or coins that could be traded for advantages while playing the game. The developer imagines this as an order service that could be invoked directly from the app. So to try out this idea, our hero stays late one evening developing a prototype. The prototype exposes a REST API through API Gateway. And since fulfilling the order process will depend upon some legacy billing systems, for the best user experience, the order will actually be fulfilled asynchronously. The API will integrate with a Lambda function that validates the order information so it can reject bad requests early. Then it will save valid orders to an SQS queue for later processing. Now the Lambda function is custom business logic, and it will be the same regardless of the technology we use to deploy the app. So let's discuss that right up front. It's relatively simple, it's written in JavaScript, and it really only has two steps. It validates the message, and it saves the message to a queue. Let's look at those functions in a little more detail. For the sake of the prototype, the validate message function just confirms the existence of two required attributes, product and quantity. The write queue message is a single line call to the send message function of the SQS queue. Now our developer is pretty smart. They build their infrastructure using CloudFormation so they can reproduce it in the future. They begin with creating the API Gateway's REST API, a Lambda function, and an SQS queue. And along the way, CloudFormation reminds them that they need a few more resources, things like an IAM role and policy, or a gateway stage, etc., until before they're finished, they've actually had to deploy 16 total resources and write 250 lines of YAML. But they finished the demo, and the next morning they gave it to the Lanager. Let's go ahead and take a look. So here is our hand-coded prototype stack. You can see the 16 resources. Within there you see the three big ones, the API Gateway REST API, the Lambda function, and finally the SQS queue. Now we're going to need the endpoint of the API Gateway to invoke it. In this case, it's an output of our stack, so we'll copy it from here. And we're going to use a program called Postman to invoke the API. If you're unfamiliar with Postman, you can think of it as a graphical user interface in front of curl. So let's create the URL for our call. It's the base URL plus an orders resource that we created. And since it changes state on the back end, we'll use a post method. Let's confirm that our body has the two required fields, product and quantity, and then we'll click Send to invoke the API. In the lower pane, you'll see the results, in this case, status OK, and a message of order accepted. What if we didn't send the correct attributes? Let's purposely corrupt our request body and change our attribute name. Then when we invoke the API, we get back status failed, invalid order data. So we'll fix our attribute name, and we'll change gems to coins just for fun, and invoke the API again. Status OK, order accepted. So we've invoked the API 3 times, twice successfully, so there should be 2 valid orders in our orders queue. So here's our hand-coded queue. We'll go to Send and Receive Messages, and we'll scroll down to the Receive Messages section, where we see there are 2 messages available. We'll poll for messages, and we'll open one up, and we'll examine the body of the message. And there we see product and quantity. We see a valid orders message. So when the demo was complete, our hero turns to the Lanager to get their reaction. And the Lanager is greatly impressed by the demo, and this makes our hero very happy. But then the Lanager says, let's get this into production right away. And suddenly, our hero is less excited. And now we see the challenge for our hero, and the conflict at the center of our fairy tale. Because the prototype was created in a single evening, and our hero knows there are some fundamental issues that stand between it and production. Here are just a couple of the issues our hero knows need to be addressed before the company could even think about putting the system into production. First, our IAM policies are overly loose, both in terms of the actions they allow and the resources they address. Second, in spite of Amazon's advice to encrypt everything, our SQS queue is not encrypted. There's no authorization mechanisms protecting our API. It's open on the internet. We essentially have security by obscurity. And while Werner Vogels has told us many, many times that everything fails all the time, there's no mechanism in place for orders that can't be processed at a later time for any reason. And finally, we're going to have DevOps issues because we used a fixed name for our SQS queue and a fixed name for our Lambda function code file. We won't be able to deploy multiple stacks in a single account because they'll collide when they try and create queues with the same name. And if we upload a new file with new Lambda function code, because it has the same name, an update stack command will not deploy that code. Now, I'm going to go out on a limb and suggest that our hero is not unique. We've all committed some or all of these sins when writing CloudFormation templates quickly. To avoid these issues, our hero could have created an architecture that looks like this. In this version, the API gateway is protected by an Amazon Cognito user pool. The Lambda function has more tightly defined roles. A KMS customer master key encrypts the SQS queue. And an SQS dead letter queue collects any failed orders for special handling. But the goal of the prototype was to quickly, and I want to emphasize that, quickly create an experiment that demonstrated the viability of adding an order service to the game app. In that regard, it was successful. To have spent hours of extra time addressing all of these issues for the prototype would have prevented getting our answer quickly. Maybe prevented getting our answer at all. And for a prototype that doesn't handle any real customer data, none of these introduce significant risk. But whenever we deploy an architecture that looks like this, it makes us uncomfortable, and rightfully so. Which leads us to the key part of any fairy tale, when the hero says, I wish. Gee, says our developer, I wish there was a way to build my architecture faster, but also following best practices. Now in fairy tales, this wish might be granted by some talisman or amulet, such as a handful of magic beans. In our fairy tale, those magic beans are the AWS Cloud Development Kit and the AWS Solutions Constructs. Let's start with the CDK. It allows you to define your architecture using a high-level language like TypeScript or Python or Java. You define objects in your source code, compile, then when you run your program, those objects generate CloudFormation YAML, which are assembled into a template and deployed as a CloudFormation stack. In this way, the CDK provides a higher level abstraction over the native YAML or JSON in a template. Now, what do I mean by a higher level of abstraction? Now, people used to write their programs in assembly language by hand. I got some old-timer friends that still brag about that on MySpace. But our industry became much more productive when higher-level languages provided a layer of abstraction over the dense machine language. And we'll see the same thing as we create abstractions over the YAML and JSON of a CloudFormation template. Let's look at some actual CDK code. When this code is deployed, it will generate CloudFormation YAML that creates a new SQS queue. The first argument to any CDK constructor is the stack where this resource should be deployed. The second is a text name for the resource in CloudFormation. CDK objects have sensible defaults defined for all settings, but they also provide the ability to override any of the default settings during instantiation. So the third argument to any CDK constructor is a properties object where you specify any non-default initialization values. Let's look at how coding this in a higher level language is going to allow for more dynamic architectures. Suppose we want to deploy different resources in different environments, say 1 queue in dev, 3 in test, and 5 in production. We could hack something together in YAML that would work, but it would be very brittle and it would be limited in its options. On the other hand, if we were trying to accomplish something like this in a high level language, we could do something like this. We could create a loop that creates queues based on some incoming parameter value. So what was tricky and brittle in YAML becomes trivial in a language like TypeScript. Actually, everything gets easier. No more YAML functions to concatenate strings. We can do it with the native string handling functions in our language. But it's when you have multiple CDK objects that work together when it really starts getting good. When you want to link different CDK objects, CDK automatically creates the code that allows them to work together. This code creates a new SNS topic and defines only the name. Then it creates a subscription for the SQS queue we defined on the earlier slide and signs that subscription up to receive messages from the SNS topic. So between the last two slides, we created an SQS queue that receives messages from a new SNS topic. Now that odd subscription line hides a lot of complexity. That line by itself is responsible for creating 25 lines of code in the final YAML template. So you can see how the CDK allows us to create our CloudFormation faster and more dynamically. Plus, since the code is written in standard language, you can write unit tests in frameworks like Jest or JUnit. But even to reproduce the original prototype, our hero still has to know and deploy the same 16 resources, and more if they want to address the issues we discussed. So our hero can develop its CloudFormation much more quickly this way, but the temptation to take shortcuts still exists. That's why we want to use AWS Solutions Constructs to help us avoid those shortcuts and build it right. AWS Solutions Constructs are a library of common patterns built on top of the CDK. Now, when we say common patterns, these are service combinations we've seen customers implement for countless workloads. Things like an S3 bucket triggering a Lambda function, or an SQS queue subscribing to an SNS topic that we just saw. They address problems that are not only solved, but solutions that have been built and deployed everywhere, so they don't just relieve you from reinventing the wheel, you don't even have to re-implement the wheel. With Solutions Constructs, you reduce the number of objects you need to create in the CDK, and you ensure that best practices are followed both for individual services and for the relationships between services. So, if the CDK is a high-level language that's compiled in a native CloudFormation, think of AWS Solutions Constructs as a high-level library like Hibernate or Express or jQuery that give you powerful capabilities within that language. Let's get back to our hero's prototype and look at the one they would have preferred to create. Let's explore how to do that using Solutions Constructs. To create our prototype, we're going to use two constructs. First is Cognito to API Gateway to Lambda. This creates an API gateway that's protected by an Amazon Cognito user pool. That API gateway is integrated with a Lambda function that's protected by tightly defined IAM roles. Now remember, the name and the diagram only show the key services that explain the functionality. In reality, there are many more resources deployed by the construct. The second construct is Lambda to SQS. This creates a Lambda function that can write to a new SQS queue. And since constructs enforce best practices, by default, it will encrypt the queue and set up a dead letter queue. Now this highlights a key aspect of Solutions Constructs. Each of these constructs can launch a brand new Lambda function as part of their instantiation, but that's not what we want here. We want a single function that's both integrated with the API and that writes to the SQS queue. To accomplish this, we can configure the second construct to not create a new Lambda function, but to point to the existing Lambda function that's being created by the first construct. Now this capability is crucial. It's because of this capability to link between solutions constructs that you can chain multiple patterns together to create more complex architectures. Let's look at a little more code. Solutions constructs are multi-service, so they encapsulate lower-level CDK objects representing each of the deployed resources, and they let you override the default settings for each of them. So for the prototype, here are the properties we will set for our internal services. For the user pool, we'll allow any type of authorization flow. Whenever we declare a Lambda function, we need to tell the CDK where to find the code to deploy for the Lambda function. In this case, we're pointing to the code we looked at a very early slide in this presentation. Finally, for our API gateway, since we explicitly defined the API, we don't want the more general proxy Lambda integration. So we'll set proxy defaults, and we'll set our authorization type to cognito. Now let's instantiate our objects. First, we'll instantiate the cognito to API gateway to Lambda construct. Now, just like a lower level CDK object, the third argument to a solutions construct constructor is a properties object. It's through this properties object that we provide the property values for the internal services, the things we showed on the previous screen. Once we've created our API in our CDK code, we can execute calls that create the orders resource and the post method on that resource. Finally, once our API is fully defined, we call add authorizers to ensure that every method we create is protected by an authorizer. Finally, we define the second construct, Lambda SQS. The only property we define here instructs the construct to use an existing Lambda object, in this case pointing to the Lambda function created by the previous construct. For all other aspects, we want the default behavior, including creating a dead letter queue and encrypting the queue. So let's go ahead and take a look at our new prototype. Here's the actual code in context. Every CDK resource and solutions construct is defined in the context of a CDK stack object. So first we define the properties for our internal services, the user pool, the Lambda function, and finally the API gateway props. Then we're going to go ahead and instantiate our constructs. First, the cognito to API gateway to Lambda, where we send in our properties. Then we add the orders resource and the post method, and add an authorizer to all of our methods. And finally, the Lambda to SQS construct, and we tell it to point to the Lambda function created by the API construct. Now this is a standard TypeScript program, so it compiles like any other TypeScript program. npm run build. Once it's compiled, we run it in the context of the CDK with a CDK deploy command. So this runs your application, which generates your CloudFormation template. It then asks you if you want to create all of the resources that the template will create. We'll say yes, and then it will go ahead and do launch the CloudFormation stack. Now this takes a little while, so like a cooking show, I pre-baked a stack which we'll now pull out of the oven to enjoy. Here is our pre-baked stack. The first thing I want to look at is the template, so I can show you one of the policies we create. So here's a policy, and you can see that now we more tightly define the actions, and we more specifically describe the resources. Let's look at our SQS queue. So if we scroll down for the details on our SQS queue, we find under encryption that it's now encrypted by a customer master key, and we've set up a dead letter queue to accept orders that can't be processed. Let's look at our API. We'll go to the API gateway, we'll look at our post method, and we see on our method request that it is now protected by an authorizer. So digging a little deeper, we'll go into our authorizers, and we see that authorizer is a Cognito user pool. So now it's time to invoke our API. So we're going to go to our stage so we can grab the URL for our API, and we'll return to Postman to invoke our API. We'll set up the URL with our base URL and our orders resource, and once again, a post method. Now notice the new authorization header that we've got this time. Before we began the session, I created a new user in the user pool and an authorization token for that user. That authorization token is the value found there in the header. Before we invoke the API, let's confirm we have product and quantity in our body. And now let's call our API. Status OK, message order accepted. What if we don't send the authorization information and call the API? We get back unauthorized. So we'll turn it on one more time, invoke it one last time, and we get back status OK. So we've invoked the API 3 times, twice successfully, so there should be 2 valid orders in our orders queue. So we'll return to our queue, to the receive messages section, and we see there are 2 messages available. We'll open one, we'll look at the body, and we see product and quantity, a valid orders object. So our API works as expected. It's protected by a Cognito user pool, and it delivers valid orders to our orders queue. So by going with constructs, we've deployed the entire prototype with less than 15 lines of code, as opposed to the original 215-line template. And at the same time, we eliminated all the shortcomings in the original version. For anyone who's curious, the 2 solutions constructs we used actually created 481 lines of raw YAML. But let's not forget, the prototype just deployed the acceptance of the orders. There's still infrastructure required to process the orders. So how could our hero go forward? Well, now our hero is wise in the way of the CDK and solutions constructs. A quick review of the solutions constructs library reveals the SQS Lambda construct, which attaches a Lambda function to an SQS queue. So our hero knows that they could create the processor with that construct by hooking a Lambda function up to the SQS queue. Let's take a look at how that might look if we were to write that code. Now that we've seen several constructs, the actual implementation of the order processor should look familiar. The first 3 lines of code on this screen are code we already wrote. That's the code that creates the Lambda to SQS queue that writes the valid orders to the queue. But the new code is instantiating the SQS to Lambda construct. In the properties object, we tell it to use an existing queue object, and we point it to the queue created by the order queue construct. We also point it to the code for a new Lambda function that will process the orders. This is code that our hero will still have to write. Now, this is another great example of the power of chaining constructs together to make more complex systems. We add the infrastructure needed to process orders with a single code command. Our hero could expand the architecture with a completely new feature in minutes and deploy the entire architecture with less than 60 lines of code. But let's compare the 2 prototypes we did write. The original prototype took more than 250 lines of YAML. The new prototype required less than 15 lines of TypeScript. The original prototype took hours to write. The second one was complete in less than an hour. The first prototype deployed 16 different resources, each of which had to be hand-coded. The second prototype deployed 21 resources, and we only had to create 2 TypeScript objects. That's just how much faster it was. How much better was it? Well, we now have more tightly defined role definitions for better adherence to the principle of least privilege. Our original queue was not encrypted. Our new queue is encrypted. Whereas there was no mechanism to handle failed orders before disappeared into the ether. Now they get moved to a DL queue so we can process them. Our original prototype was exposed to the internet. Our new prototype has a Cognito user pool protecting the endpoint. And finally, we're in a much better DevOps situation because we can deploy multiple stacks to a single account, and we can deploy new Lambda code easily. If you look at the right column, you realize the term prototype has really lost its meaning. It's really just an early iteration of a full-fledged production system. Thanks to the CDK and solutions constructs, our hero now thinks of prototypes in an entirely new way. No longer are they second-class architectures that are less secure and less functional than a production application. So from that day forward, throughout all the land, developers and managers alike rejoice in rapidly generated, full-featured prototypes. And they all lived happily ever after. Now, while that might be the end of our story, it's not the end for us. For if our tale has a moral, it's a call to action. How can we stop writing infrastructure as code in native JSON or YAML? I used to be pretty good at CloudFormation, but now that I'm comfortable with the CDK, I don't think I'll ever write raw CloudFormation again. In fact, when I wrote the template for the original prototype in this presentation, I actually wrote it using the CDK, then I hand-edited the template to reintroduce the shortcuts. The key is to start now, so the next time you face a CloudFormation project, you're ready. Look for this blog post. It takes you step by step from installing the CDK through launching a scalable data ingestion system built on Kinesis data streams, Lambda, and DynamoDB. Or if you want to learn for yourself, go straight to the docs for the CDK and Solutions Constructs. Finally, check out the other CDK Solutions Constructs reInvent session being given by my colleague Ryan Hayes. So thanks for spending some time with us today. I hope you got something out of it. And please, take a moment to fill out the session survey so we know what you thought of this session.